this module, you will learn about the potential energy stored in a stretched or compressed spring. Consider a block attached to a spring placed on a smooth horizontal surface. The other end of the spring is attached to a rigid wall. The position at which the spring is at rest initially is considered to be the mean position, with no displacement of the spring. Then, the spring is compressed and released. You can observe the spring oscillating to and fro from the rest or mean position. The displacement of the block is always measured from the mean or rest position. The spring here is under the action of a variable force, known as the spring force, which always acts towards the mean position or in the opposite direction to the displacement. When the spring is stretched, the displacement is positive. When the spring is compressed, the displacement is negative. The spring force is the restoring force which is responsible for bringing the block attached to the spring back to its mean position. The spring force F is directly proportional to the displacement x from the mean position. Thus, we see that the spring force F is proportional to minus x. We say minus x as the spring force is always directed opposite to the direction of displacement. Or, spring force F is equal to minus kx, where k is the spring constant. Let this be equation 1. In equation 1, F is equal to minus kx, which represents the force law for the spring known as Hooke's law. Work done W by the spring force is denoted by the expression integral F dx in the limits 0 to xm, where xm is the maximum displacement of the spring. Let this be equation 2. Since the spring force F is equal to minus kx, we get W is equal to minus integral kx dx in the limits 0 to xm. Let this be equation 3. On integrating equation 3, we get W is equal to minus k into x square by 2 in the limits 0 to xm. Thus, we get the work done by the spring force equal to minus half kxm square. Hence, the work done by the external elongating force will be plus half kxm square. This is the work done by the external elongating force against the spring force, and hence is stored as potential energy in the spring, as given by equation 4. Work done by the spring force can also be calculated by the area covered under the graph of displacement x during elongation or compression taken on the x-axis and the corresponding spring force F taken on the y-axis. The area of the shaded portion indicates the work done by the spring force. In equation 3, W is equal to minus integral kx dx in the limits 0 to xm. We know that the initial displacement is 0 and the final displacement is xm. Instead, if the initial displacement is x1 and the final displacement is x2, then the work done W by the spring force would be equal to the negative of integral kx dx in the limits x1 to x2. Let this be equation 5. then the work done by the spring force will be equal to half kx1 square minus half kx2 square. Let this be equation 6. Equation 6, where W is equal to half kx1 square minus half kx2 square, indicates the work done by the spring force. Then the work done by the external force W will be equal to half kx2 square minus half kx1 square. Let this be equation 7. Now if the spring is compressed to x2 and brought back to x1, then the work done by the spring force according to equation 7 will be half kx1 square minus half kx1 square, since the final position is the same as the initial position. Then the work done will be equal to 0 as in equation 8. This proves that the spring force is a conservative force, since the work done for a closed path or round trip is 0. Thus, we define the potential energy V of x of the spring as 0 when the system of the block and the spring is in equilibrium position. For any extension or compression x of the spring, we have V of x is equal to half kx square. Taking the derivative of the equation of potential energy of the spring, we get minus d by dx V of x is equal to minus d by dx half kx square. On further simplification, we get f of x is equal to minus half k into dx square by dx. Thus, by doing the derivation of the equation of potential energy of a spring, we can easily verify the equation for the spring force as f of x is equal to minus kx as shown. According to the work energy theorem, the work done by a net force on an object is equal to the change in its kinetic energy. That is, F delta x is equal to delta k, where F is the net force, delta x is the displacement, and delta k is the change in kinetic energy. Let this be equation 9. Now if the forces acting on the body include both a conservative force Fc and non-conservative force Fnc, then the equation 9 can be written as Fc plus Fnc delta x is equal to delta k. Let this be equation 10. Simplifying, we get Fc delta x plus Fnc delta x is equal to delta k. Since Fc delta x is equal to minus delta v in equation 10, we get minus delta v plus Fnc delta x equal to delta k. Let this be equation 11. We have Fnc delta x equal to delta of k plus v. Let this be equation 12. Since k plus v is the total mechanical energy of the body, which is the sum of the kinetic and potential energy of the body, equation 12 shows that the work done by the non-conservative force is equal to the change in the total mechanical energy of the body. You have now reached the end of this module. In this module, you learnt that the spring, when stretched or compressed, comes under the action of a variable force known as the spring force. The spring force is the restoring force responsible for bringing the block attached to the spring back to its mean position. Spring force F equal to minus kx, where k is the spring constant, represents the force law for the spring known as Hooke's law. Work done by the spring force is W is equal to minus half kxm square. The work done by the elongating force is W is equal to plus half kxm square. The work done by the external force is against the spring force and hence is stored as potential energy in the spring. The spring force is a conservative force as the work done for a round trip or closed path is 0.